culture. Thank you for the organization. It's a great opportunity to meet everybody. This is Patrick, my postdoc, previous PhD. So my topic is quite different, very in a microscope, intracellular trafficking. So I will explain. This is very important to unlock the potential of RNA. So some of the content Gavin already covered, but let me, does not work. Next one. So we have here we have heard lots of information that RNA has huge potential endless and a software for the life, right? I love this topic since the end of 2020 when a journal asked me to explain the formulation, what's the challenge, what's the success. So I do have a review, very highly cited, although I did not do much about RNA. I did a little bit work on plasmid DNA, but the formulation principles are really same as what I'm doing. So I was invited to write that review, and a week later, the mRNA vaccine was authorized. So that was really interesting. So all about this software, we know, but we have a limitation. So we do need to have hardware to deliver the software into the place. So we know how the formulation is made. So to wrap them so that we can deliver into the cells to translate the information. My students tend to ask, what's the difference between lipid nanoparticles, LNP, and the liposome? Because my research theme is liposome. So actually, the only difference is because the RNA is really negatively charged. It's essential to have ionizable lipids. This is the key. This is like the software, but you have a switch, and to get the RNA into the particles, but also deliver release into the cells. So it's actually it's an evolution from the liposome. So that lots of things are in common. We do know how to add ligand, right? Some people already started doing that. So that hopefully increase the target. And we know lots of routes of administration, but no matter what's the route of administration, we do need to send the RNA or a small interfering RNA into the cells, like a ribosome for mRNA, or into the cytosol. So that's the aim, to deliver into the cells, but also need to be released. That's why the intracellular trafficking is very important. Some people also ask me, what is called intracellular trafficking? So actually it's enter the cells and goes out the cells. Hopefully we can make it stay in the cells. However, it does not always work like our way. So in a simple way, endocytosis, ideally endosome escape, or lysosome escape, and no excitosis. But excitosis quite happen a lot. This is a graph that Patrick made to simplify the process. But even including the endocytosis, there are so many ways to get into the cells. And then the endosome escape, currently their rate is really, really small. Furthermore, if they are not released, they could be sent out. Excitosis, and this is a high number here also. Some people have done that. Although the excitosis that could be reused, recycled, however, it's not bioavailable. And that's a simple story. This is a paper we just recently published. We look at the different pathways to get into the cells, but also sent out by the cells. we are not going to have that. So my research actually focuses on oncology. Our strategy is, first of all, get the nanoparticles into tumors, and then try to focus on cancer cells, and then release the chemotherapies into cells, into the cytosol, that hopefully to overcome the drug resistance. So that's our strategy, but this is exactly what we need to do for the RNA drugs. So we have lots of collaborations, with the clinicians, biologists, chemists, and we have been doing for quite a long time. Our tool, as I said, my main job is liposome. So the original lipid nanoparticles. But we also look at extracellular vesicles or exosomes, so use these as tools. Our strength, first of all, we pack, we develop the strategies to pack the actives. It depends on the chemistry, how to pack inside the nanoparticles. And also we know how to modify the surface so that recognize the target cells. And then we have some triggers try to release the content, the payload, into a different organelle, depends on the application. So this is the whole trafficking process. This actually involved 40 PhD, master, and postdocs work. So time flies. 15 years just passed. Where is it? Okay. So people visited School of Pharmacy. They normally very surprised. Oh, how could you have so many, so well-equipped facilities at School of Pharmacy? If you come to Auckland, please visit us. We have all the equipment. We are going to have the molding microfluidic. We have an older style one, but we have a new one. Going to have others like nano spray dryer or freeze dryer. We have all, and also cell facilities. We are surrounded by the faculty, well equipped with imaging technologies. So just quickly to wrap, that will be essential for the RNA drug delivery. So this is just a couple of, this is an example that with the conventional liposome, you can see the green color is entrapped in the lysosome or endosome. But for our new liposomes, after achieving endosome escape, you can see the green color is spread through the cytosol. Yeah. We also look at what's the pathway. So we have protocols to look at how the nanoparticles get into the cells. They could end in different fate. Yeah, this is the example of an extracellular vesicle. If there's no modification, they really just stuck in their can't see that. You can see the red, so that's the natural extracellular vesicle. The red is the drug. After 8 hours, they still stuck in the lysosome or endosome. After our modification with the liposomes, they fuse together, they become very capable to release the content. So over the years, we do develop lots of imaging technologies, and now I'm going to let Patrick to do this. So this is just go up.
I'm just going to quickly showcase some of the stuff that we do as well. So in the zone entrapment, obviously a bit of a problem. We have some confocal, we have some confocal images over here, and we can see that our vesicles, which is labeled in red, actually gets entrapped inside the lysosomes, which is under the green. And over a whole full hour, it's still trapped inside, and we can see this with a scatter plot correlation that the entrapment it just stays inside and doesn't go anywhere. However, with our newly developed endosome escape vesicles, we can actually see that very rapidly, within 20 minutes, we can see a little bit of our vesicles start to escape from the lysosomes already. And by the first hour, we can see a huge difference in the vesicle escaping the lysosomes. Same, we can see the scatter plot over here. Now the scatter plot is nice because we can actually quantify all of that with a correlation, and we can see the entrapment slowly, our vesicles slowly staying inside of the lysosomes, but with our formulations, they're able to escape slowly out of the side of the lysosomes into the cytosol. But before all that happens, the vesicles need to get into the cells. So we also have different methods to increase the uptake of our vesicles into the cell network. Over here, we're looking at breast cancer, glioblastoma cells, and we're using RGD to target these cells and increase the cellular uptake. And over here, we see that there's a low uptake of the vesicles into the cells with our classical vesicles, but if we modify them with the targeting ligand, we actually see a significant increase in uptake into the lysosome and a subsequent release into the cytosol. And with the graph over there, we can actually see and quantify the fluorescent signals, and we can see a significant increase in that release, uptake of our vesicles into the cell. And over here, similar image from before, so we're just loading the vesicles over here, treating them with the cells, but more importantly, over here what we can see the RGD functionalized liposomes here are also able to carry and increase the amount of drug, which is doxorubicin, into the cell, and we see the greater release into the cytosol over there. And again, if we quantify the fluorescent signals, we can see that the ligand targeting vesicles increase cellular uptake and also increase the delivery of our active drug into the cytosol. And more recently, we've actually been working on 3D cell models. So not quite in vivo yet, but we've got primary cell spheroid tumor models, and we can actually see increased penetration of our doxorubicin drug deeper and deeper into the cell over here. So conventional liposomes have the problem with being trapped inside the cells, so we have our pH-sensitive particles. A couple of methods that they can actually escape from the endosome. Mostly, we're probably concerned about the proton sponge effect with LNPs. So just some work on the proton sponge effect. We see at the left-hand side, the 5-minute mark, our endosomes, which are stained in green, they don't actually see a whole lot of uptake of our liposomes. But over at about the 60-minute mark, we actually see the rupture of the liposomes and releasing our encapsulated doxorubicin drug. Yeah, so tracking that. And yeah, so we have a pH-sensitive liposomes and so yeah, sure. Okay. So yeah, to build up onto that.
So the last one is the excitosis. Excitosis is a significant limitation for the current LNP. From our liposome research, we found that the pH sensitivity could enhance the release in the cytosol, but also prevent the excitosis, so keep the content inside. Very limited study available, but I thought we could control some of the organelles inside the content, and we can control the excitosis, keep the payload available for the cells. Yeah, that's a quick rec about intracellular trafficking. We didn't really get deep into the content. Yeah, actually, we don't know what to talk. However, this is really limited into the cells, cell level, and the other things are very important to consider: the route of administration and the PK by distribution of the nanosystem. So even despite the localized injection, it could still end in the liver, or that is due to the other like lymphatic drainage. It could come to the liver, the Kupffer cells that although this could still generate some antibody proteins, however, it will be a different story. Actually, the formulation, there are many ways to improve. For example, the PEG, the pegylation, so 1.5%. This is much lower than the cancer nanomedicine. However, that's to promote the cellular uptake. But maybe also it's a limitation because that tend to get catch by Kupffer cells. Yeah, some solutions here. I'm happy to discuss when we have time. And the stability, yeah, perhaps lots of variables we could work on that, like in P ratio that could change the half-life itself. The lipid stability that governs to make it stable or less stable, so that's a balance. With that, I think everybody expects to leave. So thank you very much for having us. Throughout the 15 years, we got a lot of support and many collaborators, students. Thanks, everybody. Thank you, guys.